Introduction and Global Reach Overview. Welcome to our comprehensive exploration of Azure ExpressRoute Global Reach. This revolutionary technology transforms how we connect multiple on-premises sites through Microsoft's global backbone infrastructure. Traditional site-to-site connectivity required complex VPN tunnels or expensive MPLS networks. Global Reach eliminates these challenges by allowing direct connectivity between ExpressRoute circuits in different locations. Think of it this way. Instead of routing traffic from your New York office to London through your Azure virtual networks, Global Reach creates a direct, private connection using Microsoft's backbone. This means lower latency, higher throughput, and simplified network architecture. The key benefits we'll explore include direct site-to-site connectivity without hub routing, leveraging Microsoft's global backbone infrastructure, simplified network topology and management, enhanced security with private connectivity, and reduced latency between global locations. This presentation covers the complete implementation from planning through deployment, with real-world examples using New York and London as our primary sites. Global Reach Architecture. Let me walk you through the architecture that makes Global Reach so powerful. The diagram shows how Microsoft's backbone becomes your private network infrastructure. In traditional setups, traffic from New York to London would typically flow through ExpressRoute to Azure, and then back through another ExpressRoute circuit. With Global Reach, we create a direct connection between circuits. The key architectural components include ExpressRoute circuits, which are your dedicated connections to Microsoft. The Microsoft backbone, which is the global infrastructure connecting regions. The Global Reach connection, which is the logical link between your circuits. And BGP sessions, for route exchange between your networks. Notice how this creates a hub-spoke topology with Microsoft's backbone acting as the hub. Your on-premises networks become spokes that can communicate directly through the Microsoft network. This architecture eliminates the need for complex routing through Azure virtual networks, while maintaining the security and performance of private connectivity. Prerequisites and requirements. Before implementing Global Reach, we need to understand the specific requirements and how they differ from standard ExpressRoute connectivity. The table shows critical prerequisites. Notice that both circuits must have private peering configured. This is the foundation that Global Reach builds upon. Geographic considerations are crucial. Both circuits must be in Global Reach supported regions, and there are specific requirements for cross-geographic connections. From a technical perspective, you need standard or premium circuits only, a minimum of 50 megabits per second bandwidth with the maximum limited by the smaller circuit. Unique ASNs for each location, and non-overlapping subnets are required. Security requirements include proper authorization key management and RBAC permissions for Global Reach operations. The comparison with traditional connectivity shows significant advantages in complexity reduction and performance improvement. Multi-site connectivity design. Designing multi-site connectivity with Global Reach requires strategic thinking about your network topology. The diagram illustrates different approaches you can take. The hub-spoke model designates one location as the primary hub, in our case, New York. All other sites connect to this hub, creating a centralized routing architecture. Regional clustering is particularly effective for global organizations. You might have an Americas hub in New York as primary, an EMEA hub in London as regional, and an APAC hub in Singapore for future expansion. Each approach has trade-offs. Hub-spoke minimizes the number of Global Reach connections but creates dependency on the hub. Mesh topology provides redundancy but increases complexity and cost. Consider bandwidth requirements carefully. The hub location needs sufficient capacity to handle traffic from all spokes, while spoke-to-spoke traffic still flows through the hub in this model. For our implementation, we're using New York as the primary hub with London as a regional hub, allowing for future expansion in both regions. Strategic topology planning ensures your Global Reach implementation scales effectively and meets performance requirements. The connection patterns shown represent different strategic approaches. The star pattern centralizes everything through one hub, while the regional clustering approach distributes load across geographic regions. Key planning considerations include latency requirements where hub placement affects global latency, bandwidth distribution where hub circuits need higher capacity, redundancy planning with secondary hubs for failover, and growth accommodation for easy addition of new sites. Our recommended approach uses regional hubs to minimize latency and distribute load. New York serves America's traffic while London handles EMEA requirements. This topology planning directly influences our circuit sizing decisions. New York gets 10 Gbps as the primary hub, while London gets 5 Gbps as a regional hub. The pattern also prepares us for future expansion into APAC regions without requiring architectural changes to existing connectivity. Now we move into implementation, starting with creating our primary ExpressRoute circuit in New York. This circuit will serve as our America's hub. Let me walk through the Azure AZ command in detail. We start with AZ Network Express Route Create, which is the base command for creating ExpressRoute circuits. The -- resource group ExpressRoute-RG parameter specifies that we are placing this circuit in a dedicated resource group for all our ExpressRoute resources, which helps with organization and management. The -- name NYC-ExpressRoute-primary gives our circuit a descriptive name that clearly identifies it as the New York primary circuit. The -- peering location New York parameter tells Azure which ExpressRoute location we want to use. This should be the closest location to your actual office for optimal performance. The -- bandwidth 10,000 parameter sets our circuit to 10 gigabits per second, which reflects our hub role. This circuit will carry aggregated traffic from multiple locations. The -- provider Equinix specifies our chosen connectivity provider. Equinix has excellent presence on the East Coast and reliable service. The -- SKU family metered data means we pay for actual data transfer rather than unlimited. And -- tier premium is crucial because only premium circuits support global reach functionality. The -- location East US parameter specifies the Azure region where the circuit metadata is stored. Finally, the -- tags parameter adds metadata to help track this resource. We are tagging it as production environment, part of the Global Reach project, and identifying its role as primary hub for management purposes. The expected output shows the service key you will provide to Equinix. The circuit provisioning state is enabled, meaning Azure has created the circuit, and provider provisioning state is not provisioned, because Equinix has not completed their cross-connection yet. Let's discuss the secondary circuit creation in London. Our London circuit serves as the regional hub for EMEA operations. Let me explain the command and how it differs strategically from our New York setup. The command structure is identical to New York but with regional specific parameters. We use AZ Network Express Route Create with Resource Group ExpressRoute-RG to keep all circuits in the same resource group for unified management. The name London ExpressRoute Regional clearly identifies this as our London regional circuit. Notice we use regional instead of primary to indicate its role in our hierarchy. The peering location London connects us to the London ExpressRoute facility. The key difference is the setting, bandwidth 5000, which sets this circuit to 5 Gbps instead of 10 Gbps. This right sizing reflects London's role as a regional hub rather than the global primary hub. It provides sufficient capacity for EMEA traffic while managing costs effectively. We're using provider BT instead of Equinix, which gives us provider diversity. BT has excellent connectivity within the UK and provides geographic diversity from our US provider. The location UK West parameter stores the circuit metadata in the UK West Azure region for optimal management. The SKU tier premium is essential here because standard SKU circuits cannot participate in global reach connections, especially cross-region connections like we need between New York and London. The tags include role equals regional hub and region equals EMEA to clearly identify this circuit's purpose in our global topology. This helps with cost allocation and operational management. Like the New York circuit, you'll receive a service key that you provide to BT to establish the physical connection at their facility. Private peering configuration. Private peering is the foundation that enables global reach. Let me walk through each command and parameter in detail, as this configuration is critical for success. We start with the command AZ Network Express Route Peering Create, which configures the BGP peering between your network and Microsoft. The first command configures the New York circuit. The parameters resource group ExpressRoute-RG and Express Route Circuit Name NYC-ExpressRoute-Primary identify which circuit we're configuring. The peering type Azure Private Peering parameter is crucial. This creates private connectivity to Azure services and enables global reach. The VLAN ID 100 assigns VLAN 100 to this peering session. This VLAN ID must be unique across your entire ExpressRoute deployment and different from London's VLAN 200. The primary peer subnet 192.168.1.0/30 creates a point-to-point subnet for the primary BGP session between your router and Microsoft. This /30 subnet provides 4 IP addresses. The first and last are network and broadcast, leaving 2 usable IPs for your router and Microsoft's router. Similarly, secondary peer subnet 192.168.1.4/30 creates the redundant BGP session using the next /30 subnet. ExpressRoute requires 2 BGP sessions for redundancy. The peer ASN 65001 sets your autonomous system number to 65001, which must be unique per location. The second command configures London with identical structure but different values. VLAN 200 ensures no overlap with New York's VLAN 100. The subnets 192.168.2.0/30 and 192.168.2.4/30 are completely separate from New York's address space to prevent routing conflicts. The peer ASN 65002 for London is different from New York's 65001, which is essential for proper BGP routing and global reach. These ASNs will be used to identify traffic sources and implement routing policies. These subnet and ASN choices ensure clean separation between locations while enabling global reach to establish BGP sessions between the circuits for direct connectivity. Authorization key management. Authorization keys are the security mechanism that controls global reach connections. Let's look at each command in detail, as this is critical for security. The command AZ Network Express Route Auth Create generates an authorization key on the source circuit. We use parameters such as /resource group ExpressRoute-RG and /express route circuit name NYC-ExpressRoute-Primary to target our New York circuit as the source. The /name parameter gives the authorization a descriptive name, such as London-Global-Reach-Auth, for tracking purposes. This helps you manage multiple authorizations if you have many global reach connections. The /key name parameter, for example London Connection 2024, is an additional identifier that helps with key lifecycle management. The expected output shows 3 critical pieces of information. The authorization key is a GUID that acts like a password. Anyone with this key and the circuit resource ID can create a global reach connection to your circuit. The authorization use status shows available, which means the key hasn't been consumed yet. The name confirms the authorization name for reference. The second command, AZ Network Express Route Show, retrieves the full resource ID of the New York circuit. We use the parameters /query id and /output tsv to get just the resource ID in plain text format. This resource ID, combined with the authorization key, is what the London administrator needs to create the global reach connection. The returned resource ID follows Azure's standard format: subscription/subscription ID/resource groups followed by resource group name and the circuit name. This uniquely identifies the circuit in Azure's global namespace. Security is paramount here. The authorization key should be shared through secure channels, such as encrypted email or secure messaging. Once the key is used to create a global reach connection, its status changes to used and it cannot be reused. Keys also have expiration times for additional security. Document which keys are used for which connections, as this helps with troubleshooting and security audits. Consider this key management as important as password management in your organization. Global Reach Connection Establishment. This final step brings everything together. Let me walk through the Global Reach Connection command in complete detail, because this is where all our preparation pays off. The command AZ Network Express Route Peering Connection Create establishes the Global Reach Connection. We run this from the London Circuit perspective, connecting to the New York Circuit. The Resource Group ExpressRoute RG and Express Route Circuit name London ExpressRoute Regional specify that we are creating the connection from the London Circuit. The peering name Azure Private Peering parameter tells Azure to create the Global Reach connection on the private peering we configured earlier. Global Reach only works with private peering, not Microsoft peering. The name London to NYC Global Reach gives our connection a descriptive name for management and troubleshooting. The address prefix 10.10.10.0/29 is crucial. This 29 subnet is used exclusively for the Global Reach connection between these two circuits. It provides 8 IP addresses, with 6 usable IPs for the BGP sessions and routing infrastructure. This subnet must not overlap with any networks in your topology, or you will have routing conflicts. The authorization key parameter uses the GUID we generated from the New York Circuit. This key proves that the New York Circuit administrator has authorized this connection. Without this key, the connection cannot be established. The peer circuit parameter specifies the full Azure Resource ID of the New York Circuit. This uniquely identifies which circuit we are connecting to across all of Azure. The Resource ID format includes the subscription, resource group, and circuit name to ensure absolute specificity. The verification command AZ Network Express Route Peering Connection Show checks the connection status. When successful, you will see the connection state is reported as connected, which means BGP sessions are established and routes are being exchanged. Once this completes successfully, BGP sessions automatically establish between your circuits. Microsoft's backbone handles the routing, and you can immediately route traffic directly between New York and London through the Global Reach connection. The connection typically takes 2 to 5 minutes to fully establish after the command completes. BGP route configuration and advertisement. Now that our Global Reach connection is established, we need to configure BGP routing to ensure proper traffic flow between our sites. The beauty of Global Reach is that BGP sessions are automatically established between your circuits, but you need to configure route advertisements to control which networks are accessible. Key BGP concepts for Global Reach include route filters that control which routes are advertised and received, AS path prepending to influence routing decisions for traffic engineering, community strings to tag routes for policy application, and route maps for complex routing policies and transformations. Our New York Circuit using ASN 65001 will advertise 10.1.0.0/16, while London using ASN 65002 advertises 10.2.0.0/16. This creates clean, predictable routing between sites. Route verification is crucial. You'll want to check that routes are being properly advertised and received on both circuits using the verification commands shown. Remember that BGP convergence can take a few minutes, so patience is key when validating the routing configuration. Connection status verification and monitoring. Continuous monitoring of your Global Reach connections is essential for maintaining reliable connectivity. Let me explain each monitoring command in detail. The first command, AZ Network Express Route Peering Connection Show, checks the Global Reach connection status. We specify the parameters for this command. First, Resource Group ExpressRoute RG to target our resource group. Then, Express Route Circuit name London ExpressRoute Regional because we created the connection from London. And finally, peering name Azure Private Peering, since global reach uses private peering. The parameter name London to NYC global reach identifies the specific connection we want to check, and query connection state filters the output to show just the connection status. When working properly, this returns connected, indicating that BGP sessions are established and traffic can flow. The second command, AZ Network Express Route List Route Tables, examines the BGP route table to see what routes are being learned. We target the London circuit using several parameters. First, name London Express Route Regional. Then, we specify peering name Azure Private Peering for the private peering, and path primary to check the primary BGP session. This shows the actual routes being exchanged, including networks learned from other sites through global reach. You should see routes from New York appearing in London's route table and vice versa. The monitoring command, AZ Monitor Metrics List, collects performance data from the circuit. We specify the full resource path to the London circuit. We request the metrics bits in per second and bits out per second to see bandwidth utilization. We use interval PT1M for 1-minute intervals, and set time ranges with start time and end time. This bandwidth monitoring is crucial for capacity planning. In our example, we're seeing 2.3 gigabits per second usage on our 5 gigabits per second London circuit, indicating good utilization at 46% without approaching saturation levels. Set up automated alerting based on these metrics to catch issues before they impact users. Monitor connection state changes, BGP session failures, and bandwidth utilization approaching circuit limits. Advanced route filtering and traffic engineering. As your global reach topology grows, sophisticated route filtering becomes essential. Let me explain each command in this advanced configuration sequence. First, we create a route filter using the command AZ Network Route Filter Create. The parameter -- resource group ExpressRoute RG places this in our ExpressRoute resource group. -- name NYC production filter gives it a descriptive name, and -- location East US specifies where Azure stores the filter metadata. Next, we add filter rules using the command AZ Network Route Filter Rule Create. The first rule, -- name allow production, with -- access allow, creates a permit rule. The -- communities 10.1.0.0/20 parameter specifies which network to allow. Notice this is a /20 subnet within our larger /16 network, allowing only production networks to be advertised to London. The second rule, -- name block development, with -- access deny, explicitly blocks the development network 10.1.100.0/24 from being advertised. The -- rule type community tells Azure to match based on the network address specified in the community's parameter. Finally, the command AZ Network Express Route Peering Update applies this filter to our circuit. We target the NYC ExpressRoute primary circuit and its Azure Private Peering, then use -- route filter NYC production filter to attach our newly created filter. This configuration means London will only see our production networks at 10.1.0.0/20 but not our development networks at 10.1.100.0/24. This is crucial for security. You don't want development environments accessible from other global sites. The route filtering happens at the BGP level, so blocked networks simply don't appear in routing advertisements to the global reach peer. Management networks at 10.1.200.0/24 would also be blocked by this filter since they are not explicitly allowed. Route filters are applied per circuit, so you can have different policies for different global reach connections. London might need access to some networks that Hong Kong doesn't, for example. Troubleshooting global reach connectivity. When global reach connections experience issues, systematic troubleshooting with the right commands is essential. Let me walk through each diagnostic command in detail. The first command AZ Network Express Route Peering Connection show checks the overall global reach connection health. We specify the exact connection using Resource Group Express Route-RG. Express Route Circuit Name London-Express Route-Regional. Peering Name Azure Private Peering. And Name London-to-NYC-Global Reach. This returns detailed status information including connection state, provisioning state, and any error messages. The second command AZ Network Express Route List Route Tables examines BGP routing. We target name London-Express Route-Regional, specify peering name Azure Private Peering, and path primary to see the primary BGP sessions routes. If global reach is working, you should see routes from New York appearing here. Missing routes indicate BGP issues. The third command AZ Network Express Route show checks the underlying circuit status. We use Query Service Provider Provisioning State to specifically check if the provider has completed their provisioning. If this shows not provisioned, the provider hasn't finished their work and global reach cannot function. The final command AZ Network Watcher Test Connectivity performs end-to-end connectivity testing. We specify source resource as a VM in New York, dest address 10.2.0.4 as a target in London, and dest port 22 to test SSH connectivity. This tests the complete path through global reach. Common failure patterns include authorization key expiration where the connection shows failed status, subnet overlaps causing routing conflicts, provider provisioning delays where circuits show not provisioned, and BGP session failures due to ASN mismatches. When troubleshooting, always check these in order. Circuit provisioning state first, then global reach connection status, then BGP route tables, and finally end-to-end connectivity. This systematic approach identifies the failure layer quickly. Security and compliance considerations. Global reach introduces specific security considerations that require careful configuration. Let me explain each security command in detail. The first command AZ Network Route Filter sets up compliance-aware filtering. For this command, we specify the resource group ExpressRoute-RG for our ExpressRoute resources, the name compliance filter for identification, the location East US for metadata storage, and importantly the tags environment equals production, compliance equals SOX to mark this filter for SOX compliance tracking. The RBAC command AZ role assignment implements access control. The assignee parameter global reach admins at company.com specifies a security group that should manage global reach. The role parameter network contributor gives them necessary permissions to manage ExpressRoute circuits and global reach connections. The scope parameter limits their access to just our ExpressRoute resource group, implementing least privilege access. The monitoring command AZ monitor activity log alert sets up security alerting. We create an alert named global reach changes that triggers on the condition parameter category equals administrative, meaning any administrative changes to resources. This ensures the security team gets notified of any configuration changes to global reach components. The action groups parameter specifies who gets alerted when changes occur. This should point to your security team's notification group to ensure rapid response to unauthorized changes. Network segmentation through route filtering ensures sensitive networks remain isolated. The compliance filter shown only allows specific networks to traverse global reach connections, preventing accidental exposure of sensitive development or management networks. Audit logging is crucial for compliance. Every global reach configuration change generates activity logs that can be queried for compliance reports. Set up log analytics workspaces to collect and analyze these logs for regulatory requirements. Consider additional encryption for highly sensitive data even though global reach traffic traverses Microsoft's secure backbone. Some compliance frameworks require application-level encryption regardless of transport security. Performance optimization and best practices. Optimizing global reach performance requires understanding both technical configuration and operational best practices. The optimization strategies shown can significantly improve your global network performance. Let me detail each approach systematically. Bandwidth optimization starts with right-sizing your circuits. Our New York hub at 10 gigabits per second provides headroom for growth, while London's 5 gigabits per second matches current regional needs without over-provisioning. Key optimization techniques include circuit placement, to choose locations closest to your offices, provider selection, to evaluate latency, reliability, and local presence, redundancy design, to plan for circuit and provider failures, and traffic patterns, to understand and optimize for your actual usage characteristics. Regional clustering reduces latency by keeping traffic within geographic regions when possible, while still providing global connectivity when cross-regional communication is needed. QoS configuration ensures that critical applications get priority during periods of high utilization across your global topology. Regular performance reviews help identify usage trends and plan for capacity upgrades before they become bottlenecks that impact user experience. Cost management and optimization. Understanding and optimizing global reach costs is crucial for sustainable global connectivity strategies. The cost breakdown shows the major components of global reach expenses. Notice how circuit costs dominate the monthly spend. This is where optimization efforts should focus primarily. Cost optimization strategies include right-sizing circuits to match bandwidth to actual needs plus reasonable growth projections, regional consolidation using hub-spoke to minimize total circuit count, provider negotiation to leverage multi-site deployments for better rates, and usage monitoring to track actual utilization versus purchased capacity. Our example shows $8,500 monthly for the complete New York-London global reach setup. While this seems expensive, compare it to alternatives like MPLS networks or multiple VPN solutions with their associated complexity. The global reach connection fee of $150 per month is minimal compared to circuit costs, making it very cost-effective to add connectivity between existing ExpressRoute circuits without additional infrastructure. Consider reserved instances for long-term deployments to reduce circuit costs by up to 38% with annual commitments, providing significant savings for stable deployments. Regular cost reviews should evaluate utilization trends and identify opportunities for circuit optimization or provider contract renegotiation. Scaling to multiple regions. As your organization grows globally, scaling your global reach network requires strategic planning for optimal topology and performance characteristics. The multi-region topology shown demonstrates how to expand from our initial New York to London setup to include APAC operations with Singapore as the regional hub. Scaling considerations include hub selection. Choose locations with optimal geographic coverage for each region. Bandwidth planning. Ensure hubs have capacity for aggregated traffic from multiple spokes. Provider strategy. Maintain diversity across different geographic regions. En route optimization. Minimize unnecessary hub traversals that add latency. The regional clustering approach scales efficiently. Each region has its designated hub, and inter-region traffic flows through hub-to-hub connections. This minimizes the total number of global reach connections needed. For a 3-region topology, you need only 3 global reach connections. From New York to London, London to Singapore, and Singapore back to New York, rather than 6 connections for full mesh connectivity. Consider future expansion when designing your initial topology. It's much easier to add spoke sites to existing regional hubs than to restructure your entire global architecture later. Automation becomes critical at scale. Use infrastructure as code principles to deploy and manage multiple circuits consistently across regions. Disaster recovery and high availability. Building resilient global reach connectivity requires careful configuration of redundant circuits. Let me explain the high availability commands in detail. The first command, AZ Network Express Route Peering Update, configures BGP local preference for path selection. We target the primary circuit, NYC ExpressRoute Primary, and its Azure Private Peering, then set local preference to 200, which is a high value indicating this is the preferred path. Local preference is a BGP attribute that influences outbound routing decisions. Higher values are preferred, so 200 makes this the primary path for outbound traffic from Azure to your on-premises networks. The second command configures the secondary circuit with local preference 100, which is lower than the primary. This means traffic will prefer the primary circuit when both are available, but automatically fail over to the secondary if the primary fails. The monitoring command, AZ monitor metrics list, tracks BGP availability. We specify the full resource path to the primary circuit and request the BGP availability metric with an interval of PT5M, for 5-minute intervals. This metric shows whether BGP sessions are up or down. BGP availability monitoring is crucial because it is the first indicator of circuit problems. If BGP sessions fail, traffic will automatically reroute to secondary circuits, but you need alerting to know when this happens. For complete high availability, deploy redundant circuits in each location with different providers. Configure automatic failover through BGP local preference settings, and ensure you have alternative global reach connections between backup circuits. Test failover procedures regularly by administratively shutting down primary circuits and verifying that traffic fails over correctly to secondary paths. Document recovery procedures for manual intervention when automatic failover is not sufficient. Operational excellence and future planning. Achieving operational excellence requires establishing automation and monitoring. Let me explain the future-ready configuration commands in detail. The first command, AZ Network VWAN Create, establishes Azure Virtual WAN for simplified management. We specify parameter, resource group, global networking RG, for a dedicated networking resource group, name, global VWAN for identification, location, East US, for the primary region, type, standard, for full feature support, and tags, environment equals production future ready equals true, to mark this as our evolution path. The second command, AZ Network VWAN Hub Create, establishes the VWAN Hub infrastructure. We target our VWAN with parameter, VWAN, global VWAN, name it, name, America's Hub, place it in, location, East US, and assign, address prefix, 10.0.0.0/16, for the hub's internal addressing. The parameter, SKU, standard, provides full routing and security features. The third command, AZ Network Express Route Gateway Create, creates the Express Route Gateway within the VWAN hub. We specify parameter, name, VWAN-ER-Gateway, target our virtual hub, America's Hub, and configure scaling with min scale units 2 for baseline capacity. This gateway connects express route circuits to the VWAN infrastructure. The fourth command, AZ Network Express Route Gateway Connection Create, connects existing circuits to VWAN. We target our gateway with parameter, gateway name, VWAN-ER-Gateway, name the connection, name, NYC-circuit connection, and specify the peering parameter with the full resource path to our existing express route circuits private peering. This VWAN migration strategy allows you to gradually transition from traditional global reach to the simplified VWAN management model. Global reach extends beyond pure Azure connectivity to enable sophisticated multi-cloud architectures. Organizations today often use multiple cloud providers for different workloads, and global reach can serve as the backbone for these hybrid strategies. The multi-cloud integration shown demonstrates how global reach connects your on-premises data centers to multiple cloud providers simultaneously. Your New York office connects to Azure via ExpressRoute, AWS via Direct Connect, and Google Cloud via Partner Interconnect, all through the same physical infrastructure. This approach provides several strategic advantages. You can run workloads in the most suitable cloud for each use case while maintaining consistent, private connectivity. Data sovereignty requirements can be met by keeping certain workloads in specific geographic regions or cloud providers. The key technical consideration is routing design. You'll need careful BGP community management to control which routes are advertised to which cloud providers. Some workloads may need to remain isolated within a single cloud environment for compliance reasons. Cost optimization becomes more complex but also more powerful in multi-cloud scenarios. You can leverage the most cost-effective cloud for each workload while maintaining seamless connectivity through your global reach backbone. Security considerations include consistent identity and access management across clouds, network segmentation policies that span multiple providers, and encryption standards that work across all connected environments. SD-WAN integration and hybrid connectivity. Software-defined WAN integration with global reach creates powerful hybrid connectivity solutions. Let me explain the SD-WAN configuration commands in detail. The first configuration block sets up IPSLA monitoring for path health detection. The IPSLA1 command creates an SLA probe with ID 1. The ICMP Echo 10.2.0.1 source interface Gigabit Ethernet 0/0/0 sends ICMP pings to the London endpoint through our global reach interface to monitor connectivity health. The frequency 10 parameter means we test every 10 seconds, providing rapid detection of global reach path failures. This monitoring feeds into the SD-WAN controller's path selection algorithms. The route map configuration implements policy-based routing for application-aware path selection. Route map SD-WAN policy permit 10 creates the first policy statement with sequence number 10. The match IP address ERP traffic matches traffic defined in our ERP access list. The set interface Gigabit Ethernet 0/0/0 directive forces ERP traffic through the global reach interface for guaranteed performance. Sequence 20 handles general traffic with match IP address general traffic and set interface Gigabit Ethernet 0/0/1, which routes it through the SD-WAN internet connection. The access lists define application classification. IP access list extended ERP traffic creates a named access list for critical applications. Permit TCP any host 10.2.50.100 = 1433 allows SQL Server traffic to our London ERP database, while permit TCP any host 10.2.50.101 = 3389 allows RDP to the ERP application server. The general traffic access list uses permit TCP any = 80 and permit TCP any = 443 to match general web traffic that can use lower-cost SD-WAN paths. This configuration provides intelligent path selection where critical applications get global reach performance while general traffic uses cost-effective internet paths managed by the SD-WAN solution. Azure Virtual versus WAN migration strategy. Azure Virtual versus WAN represents the evolution of global reach connectivity. Let me explain each migration command in detail to help you transition smoothly. The first command, AZ Network versus WAN Create, establishes the Virtual versus WAN foundation. We specify --resource group global versus WAN RG for a dedicated versus WAN resource group, --name enterprise versus WAN as our descriptive identifier, and --location East US for the primary management region. The --type standard parameter is crucial because it provides full versus WAN features including ExpressRoute connectivity, VPN gateways, and advanced routing. The --disable VPN encryption false maintains VPN encryption capabilities for branch connectivity. The second command, AZ Network versus WAN Hub Create, deploys the regional hub infrastructure. We target R versus WAN with versus WAN Enterprise versus WAN and create name Americas versus WAN Hub for the Americas region. The location East US places this hub optimally for our New York operations. The address prefix 10.100.0.0/16 assigns a large address space for the hub's internal routing and connected resources. The SKU standard enables full ExpressRoute and VPN capabilities within this hub. The third command, AZ Network Express Route Gateway Create, establishes ExpressRoute connectivity within the vWAN hub. We specify name versus WAN ER gateway for identification, location East US to match our hub location, and virtual hub Americas versus WAN hub to attach it to our hub. The min scale units 2 and max scale units 10 parameters configure automatic scaling for the gateway. Scale units determine throughput capacity. Each unit provides approximately 2 gigabits per second of throughput. Starting with 2 units gives 4 gigabits per second baseline capacity that can scale to 20 gigabits per second automatically based on demand. The final command, AZ Network Express Route Gateway Connection Create, connects your existing ExpressRoute circuit to the new vWAN infrastructure. We target gateway name versus WAN ER gateway and create name NYC circuit connection for the connection identifier. The peering parameter requires the full resource path to your existing circuit's private peering. This maintains your current global reach connections while adding versus WAN management capabilities. Case study. Global financial services firm. This case study examines how a major financial services firm implemented global reach to connect trading floors, data centers, and regulatory environments across 4 continents with strict compliance and performance requirements. The firm faced unique challenges including ultra-low latency requirements for high-frequency trading, strict data sovereignty regulations requiring certain data to remain in specific countries, 24/7 operations with no tolerance for downtime, and regulatory compliance requiring detailed audit trails for all network traffic. Their solution architecture used New York as the primary trading hub with 100 gigabits per second connectivity, London as the European trading hub with 50 gigabits per second for market access, Hong Kong as the Asian Pacific Trading Center with 50 gigabits per second for regional markets, and Sydney as the compliance and back-office hub with 10 gigabits per second for regulatory reporting. Implementation challenges included coordinating with multiple ExpressRoute providers across regions, implementing microsecond precise time synchronization across all sites, ensuring regulatory compliance with data residency requirements, and maintaining 99.99% uptime during the migration process. The results were impressive. Trading latency reduced by 60% compared to their previous MPLS network. Compliance reporting improved with centralized network monitoring. Operational costs decreased by 40% through simplified network management, and scalability improved with easy addition of new trading venues. Key lessons learned include the importance of detailed pre-migration testing, the value of provider diversity for redundancy, the need for comprehensive monitoring and alerting, and the benefits of automation for managing complex global topologies. Case study: Global Manufacturing Enterprise. This manufacturing case study demonstrates how global reach enabled Industry 4.0 transformation by connecting factories, research facilities, and supply chain partners across multiple continents, requiring real-time data sharing. The manufacturing company needed to connect 15 factories across 8 countries, integrate real-time production data for supply chain optimization, enable collaborative research and development between global teams, and maintain secure communications with suppliers and partners worldwide. Their business requirements included real-time production monitoring and control systems, large file transfers for CAD and engineering data, video conferencing for global collaboration, and secure partner connectivity for supply chain integration. The Global Reach solution used regional manufacturing hubs, with Detroit as the Americas Manufacturing Center at 20 gigabits per second, Stuttgart as the European operations hub at 15 gigabits per second, and Shanghai as the Asian production center at 15 gigabits per second. Individual factories connected as spokes with bandwidth sized based on production volume and data requirements. Implementation focused on industrial IoT integration, with global reach providing the backbone for sensor data collection, predictive maintenance systems requiring low latency connectivity, supply chain visibility through real-time data sharing, and quality control systems with centralized data analysis. Business outcomes included 35% improvement in supply chain visibility, 25% reduction in maintenance costs through predictive analytics, 50% faster product development cycles through global collaboration, and 20% improvement in overall equipment effectiveness through real-time monitoring. Critical success factors were careful bandwidth planning for industrial applications, integration with existing manufacturing execution systems, security measures for industrial control systems, and change management for global operational teams. Advanced Azure Service Integration. Global reach serves as the foundation for integrating advanced Azure services. Let me explain each integration command in detail. The first command, AZ Network Firewall, deploys Azure Firewall for centralized security across your global reach topology. We specify --resource group global security RG for security resources, --name global firewall as the identifier, and --location East US for the primary region. The --VNet name hub VNet parameter attaches the firewall to your hub virtual network, and --public IP firewall PIP assigns a public IP for outbound internet connectivity and management access. The second command, AZ Network Firewall Policy establishes the security policy framework. We use --name global firewall policy for identification, --location East US to match our firewall, and --SKU premium which provides advanced threat protection, TLS inspection, and IDPS capabilities for enterprise security. The third command, AZ Network Firewall Policy Rule Collection Group creates rule collections for organizing security policies. We target --policy name global firewall policy, create --name global reach rules for global reach specific rules, and set --priority 1000 which determines rule processing order. Lower numbers process first. The fourth command, AZ Monitor Log Analytics Workspace establishes centralized logging for your global topology. We specify --resource group global monitoring RG for monitoring resources, --workspace name global log analytics as the identifier, and --SKU per GB 2018 for pay per gigabyte pricing. The final command, AZ Monitor Diagnostic Settings enables network monitoring for your express route circuits. We target the full resource path of our NYC circuit, create --name network insights for the diagnostic setting, and specify --workspace pointing to our log analytics workspace. The --logs parameter configures which logs to collect. We are collecting peering route log with enabled true to capture BGP route advertisements and changes. This provides crucial visibility into global reach routing behavior across your topology. This integration provides unified security policies across all global reach connected sites, centralized monitoring and analytics for global network performance, and comprehensive logging for security and compliance requirements. IPv6 and next-generation protocol support. As organizations prepare for IPv6 adoption, global reach provides a foundation for next-generation protocols. Let me explain the IPv6 configuration commands in detail. The first command shows future IPv6 ExpressRoute peering configuration. The base AZ Network Express Route Peering create command structure remains the same, but we're adding IPv6 parameters alongside existing IPv4 settings. The traditional parameters remain and work exactly as before for IPv4 connectivity. These include Resource Group ExpressRoute RG, Express route circuit name NYC ExpressRoute primary, peering type Azure private peering, VLAN ID 100, and peer ASN 65001. The IPv4 subnets. Primary peer subnet 192.168.1.0/30 and secondary peer subnet 192.168.1.4/30. Continue providing IPv4 BGP sessions, ensuring backward compatibility with existing infrastructure. The new IPv6 parameters add dual stack capability. The IPv6 primary peer subnet 2001:DB8:1:1/126 creates the primary IPv6 BGP session using a /126 subnet, which provides 4 IPv6 addresses, equivalent to the /30 IPv4 subnet functionality. Similarly, IPv6 secondary peer subnet 2001:DB8:1:4/126 creates the secondary IPv6 BGP session for redundancy. The address 2001:DB8:1:4 is the next /126 subnet after the primary, maintaining the same pattern as IPv4. The second command, AZ Network Express Route Peering Update, configures route advertisements for both protocols. The advertised public prefixes 10.1.0.0/16 continues advertising IPv4 networks, while IPv6 advertised public prefixes 2001:DB8:1000:/48 advertises your IPv6 network range. The DNS verification commands show dual stack operation. The NS lookup type equals AAA queries IPv6 addresses for your servers, while NS lookup type equals A continues providing IPv4 addresses. This dual stack approach ensures compatibility during migration. This configuration enables gradual IPv6 adoption where applications can use IPv6 when available while falling back to IPv4 for compatibility, all over the same global reach infrastructure. Future roadmap and emerging technologies. The future of global reach involves integration with emerging technologies. Let me explain the conceptual future configuration commands that demonstrate the evolution path. The first command, AZ Network AI Optimizer Create, represents future AI-driven network optimization. We specify resource group Global AIRG for AI-specific resources, name Global Network AI as the optimizer identifier, and scope targeting our entire ExpressRoute resource group for comprehensive optimization. The optimization goals parameter, specifying latency, cost, and reliability, tells the AI system to balance these three objectives when making routing decisions. The learning mode continuous enables ongoing optimization based on traffic patterns and performance metrics. The second command, AZ Network 5G Integration Create, shows future 5G core network integration. We specify name Global 5G Core for the integration service, Global Reach Circuits listing our primary circuits that will support 5G backhaul, and edge locations identifying edge computing nodes for 5G services. This integration would enable global reach to serve as the backbone for 5G core networks, providing the high bandwidth, low latency connectivity required for 5G services across global deployments. The third command, AZ Network Quantum Security Create, represents quantum safe encryption capabilities. We specify name Quantum Safe Encryption for the security service, algorithm post-quantum crypto for quantum-resistant encryption, and key distribution Quantum KD network for quantum key distribution across the global reach network. The final command, AZ Network Satellite Integration Create, shows satellite connectivity integration. We specify name Global Satellite Backup for the service, primary circuits NYC ExpressRoute primary as the terrestrial backup source, satellite provider OneWeb for the satellite constellation, and failover mode automatic for seamless failover to satellite paths. These conceptual commands demonstrate how global reach will evolve to support emerging technologies while maintaining backward compatibility with current deployments. The foundation you have built today will adapt to support future innovations in networking, security, and connectivity.